to reduce noise and vibration in electric motors using Ansys tools. Before we dive into workflows and tools, it's worth asking, why does NVH matter so much? Let's look at the key reasons. First, comfort and regulation. Customers expect a quiet, smooth ride, and regulation is demanded. That means meeting noise and vibration requirements, reducing harshness, and complying with standards. Second, early problem detection. If we don't catch NVH issues early, things like resonance or vibration fatigue can lead to failures later on. And fixing those problems late in the process is expensive and time-consuming. And third, cost. Physical prototypes and testing are expensive. Simulation helps us cut those costs and speed up development by reducing the number of prototypes we need. Now, NVH isn't just about the motor. It's everywhere in the vehicle. We are talking about powertrain and electric motor, cooling systems and fans, tires and suspension, wind and aerodynamic interactions, structural components, etc. Simulation lets us look at all these systems individually and at the full vehicle level, so we can predict and optimize NVH performance before we even build a prototype. Traditionally, NVH validation happened late in the process, during physical testing. That's expensive and risky because if you find a problem then, it's too late for big design changes. What we are doing now is shifting that workload earlier into the design phase using simulation. That gives us 4 big advantages. It's cost-effective because we need fewer prototypes. It's faster, so we can iterate more quickly. It allows design optimization, exploring more options virtually. And most importantly, it gives us early system-level NVH insight so we can prevent surprises later on. This shift is critical for meeting today's aggressive timelines and cost targets. Before we go deeper, let's make sure we are all on the same page about what NVH actually means. NVH stands for noise, vibration, and harshness, a term that describes how mechanical and acoustic energy from systems like motors, gears, fans, or road interaction is perceived. Noise is the unwanted sound generated by different vehicle components. Vibration is the oscillation that passengers feel through the structure of the vehicle. And harshness is more subjective. It's about the perceived quality of the ride, the overall feel of the vehicle. So NVH isn't just about sound, it's about the entire experience of comfort and quality. As we mentioned earlier, noise in a vehicle comes from different sources. For convenience, we group them into 3 main categories: electrical, mechanical, and aerodynamic. On the left, you can see examples of each, and on the right, how they all combine at the system level. To control NVH effectively, we need to understand and characterize all these sources, from individual components all the way up to the full vehicle. Let's move on to some basic simulation workflows for NVH analysis using different Ansys tools. These are 4 example workflows that Ansys provides for NVH analysis. Each workflow combines specialized tools to capture the physics accurately and predict sound and vibration behavior. Let me walk you through them briefly. First, the e-drivetrain sound workflow. We start with Ansys Maxwell to calculate electromagnetic forces on the rotor and stator. These forces are then passed to Ansys Motion for a multi-body simulation of the drivetrain system, including force transfer to the housing. Finally, Ansys Sound is used for order analysis, psychoacoustic evaluation, and sound design characterization. Next, the motor sound workflow. Again, we begin with Maxwell to compute frequency-dependent forces from electromagnetic harmonics. These forces feed into mechanical for structural analysis to calculate structural response and vibration. Then, using mechanical for acoustic analysis, we predict radiated noise, and finally, Ansys Sound evaluates sound quality and compares results with measurements. The third workflow is for fan sound. Here, Ansys Fluent models the aerodynamics and acoustic sources of the fan. Then, Fluent with RBF Morph allows blade shape optimization and parametric studies. The acoustic results are processed in Ansys Sound for psychoacoustic analysis and sound characterization. Finally, the golf ball impact sound workflow. This uses LS-Dyna explicit to simulate the transient impact of the ball with a club, followed by LS-Dyna boundary element method for acoustic radiation prediction. The results are then analyzed in Ansys Sound for noise assessment and sound design. These workflows demonstrate how Ansys integrates multiphysics from electromagnetics and structural dynamics to acoustics and psychoacoustics to deliver accurate NVH predictions for electric motors and related systems. A few words about MotorCAD. Ansys MotorCAD is a specialized software tool designed for the electromagnetic design and analysis of electric machines. It focuses on optimizing and performance and efficiency of electric motors throughout their entire life cycle, from initial design to operational performance. It is great for early design because it handles electromagnetic, thermal, and mechanical analysis quickly. But the real advantage in its multiphysics coupling. It connects with Maxwell, mechanical, and Ansys sound, so we can go from electromagnetic forces to structural vibration to acoustic prediction all in one workflow. That means we get a complete NVH picture early without waiting for prototypes. Now, let's dive into the detailed workflow we'll focus on for the rest of the presentation. This is the NVH workflow implemented in Ansys Workbench. Workbench is really powerful because it lets us connect different physics in a single environment. We can transfer geometry, share mapped results between solvers, and even link parameters for optimization or sensitivity studies. Here's how the process works. We begin with Maxwell 2D, calculating electromagnetic forces at single or multiple RPMs, which are the root cause of vibration in electric machines. Then we move into mechanical, building a 3D model of the motor and housing. This step includes model analysis to identify natural frequencies and mode shapes. Next comes harmonic response analysis, where we apply those electromagnetic forces and evaluate how the structure responds under steady-state harmonic loads. It's a critical step for identifying resonance and vibration levels. Finally, we run harmonic acoustic analysis to predict how vibrations translate into sound waves, giving us the motor's acoustic performance. So this workflow takes us from electromagnetic forces all the way to sound prediction in one connected process. To make this easier to follow, we'll break the process into 4 steps. Step 1, magnetic simulation to calculate electromagnetic forces. Step 2, structural simulation, where we incorporate all forces and analyze vibration. Step 3, acoustic simulation, predicting how those vibrations radiate as noise. And step 4, sound experience, where we actually listen to the predicted sound and evaluate psychoacoustic metrics. We'll go through each of these steps in detail using this system and process as our guide. Let's start with the first step. The first step in the workflow is to calculate the magnetic forces. These forces can come from different sources: regular forces on the stator teeth, high-frequency drive switching, or even unbalanced magnetic pull. Typically, we calculate these forces in the time domain for electric machines and then convert them into the frequency domain. Why? Because the frequency representation helps us identify dominant harmonics that could cause resonance later on. So, what do we get? Radial, tangential, and axial forces. These are the inputs for the next step in the workflow. On the left, you can see the magnetic field distribution from Maxwell 2D. This shows how the electromagnetic forces are spread across the motor at different RPMs. Below that, we have the magnetic forces mapped on the geometry. On the right, the plots show the force components in the time domain and then, after FFT conversion, into the frequency domain. This is critical because it tells us which frequencies will drive vibration and noise. We continue to the second step. The second step is all about understanding how the structure responds to those magnetic forces we calculated earlier. We start with model analysis, which is a free vibration simulation. This tells us the natural frequencies and mode shapes of the motor and housing, basically how the structure wants to vibrate. It's critical because if any of those natural frequencies line up with the electromagnetic excitation, we can get resonance. Next, we bring in the magnetic forces and moments from Maxwell and apply them in a harmonic response analysis. This simulates how the motor and housing vibrate across a range of frequencies when subjected to those forces. It helps us predict vibration levels and identify critical resonance points. The results from this step feed into ERP calculation, acoustic analysis, fatigue studies, and even optimization. And because everything is integrated in Workbench, we can share CAD, mesh, and parameters easily for design studies and sensitivity analysis. After analyzing both magnetic and structural behavior, we can take it a step further with an optimization study. And here's where multiphysics really makes a difference. Instead of optimizing just the housing or just the motor, we can optimize both together using parameters from the electromagnetic and structural domains. Why is that important? Because NVH's performance depends on the interaction between these physics. Tools like Design Explorer or OptiSlang make this possible by running design studies and sensitivity analysis across multiple physics. This is how we move from good design to truly optimized NVH performance. Moving on to the third step. The third step is where we move from structural vibration to sound. The forced structural analysis gives us surface vibration, and these vibrations are what cause pressure changes in the air. Basically, sound propagation.
This one is
now,
interesting.
There are two ways to look at this. ERP, or equivalent radiated power, is a quickly approximation. It estimates the radiated noise based only on surface velocity. No full acoustic simulation is required. It's useful for getting a first idea of noise levels. But if we want full accuracy, we run a harmonic acoustic analysis. This predicts sound pressure levels, far field results, and even microphone responses. It shows directionality and gives us sound pressure levels at any location. On the right, you can see the ERP waterfall plot. This shows how radiated sound power varies with frequency and RPM, helping us spot which frequencies are the loudest. The best part? Acoustics is fully integrated into Workbench Mechanical, so the setup feels familiar. And now, let's move to the final step in our workflow. The last step is where we take all the analysis and turn it into something we can actually hear. After reviewing the ERP and SPL results, we know which frequencies are critical and where noise might be a problem. To really understand the sound experience, we export these results into Ansys Sound. Ansys Sound lets us visualize and listen to the generated sound at specific locations, inside the cabin or outside the vehicle. This is called oralization, and it's incredibly useful because it simulates how the motor noise will be perceived by passengers and bystanders. By hearing the sound and analyzing psychoacoustic metrics, engineers can make informed decisions on what to change to improve the audible experience. This is where NVH analysis goes beyond compliance. It becomes part of sound design. So that wraps up today's session. Thank you for joining and spending your time with us. If you have any questions, please feel free to email me. Enjoy the rest of the day.